Boston as a summer student there. During my time there, I was fascinated, and that was the time when we were manipulating DNA. We could actually cut and paste DNA in extraordinary time. And during that time, because I was surrounded by so many amazing people, I started reading this book called The Eighth Day of Creation. For those of you who have not read it, I highly recommend it. It really tells you how we know what we know about DNA, transcription, translation, and all that stuff. Because of that experience, I actually had a personalized autograph version of the double helix by James Watson, which I still have today. That really inspired me to go into research as a PhD student, and ended up studying the process of DNA repair. I wish I could show you pictures. You have to imagine this, right? So DNA repair, why is that important? We have about 3 billion nucleotides of DNA in our body, okay, in our cell, that needs to be maintained every day. And if you think about the developmental process, we went from a single cell organism to a body consisting of 37 trillion cells, okay? 3 billion nucleotides in 37 trillion cells. And you have to, in some way, maintain fidelity of the replication. Otherwise, we're all going to be mutated, and our genome will be incredibly unstable. And all that is done by DNA repair processes, right? And so I was fascinated by that, ended up working on that, and that was my PhD. I was going to show you some of the papers I published, but that's okay. So, still no luck, huh? Well, we can keep going. So that's my shire, right? That's the place I feel most comfortable in. The disease I'm treating, all of you know, I'm a specialist in glioblastoma, a very aggressive disease. I would point out that this is a disease, yes?
Do you want to turn the monitor around so people in front could see?
It's all right. I don't know what's happening, but it's okay. I could give a talk. I just give a talk. It's fine. So one of the things that you should know about glioblastoma, at least in the United States, is this is a disease that you could argue has influenced the political trajectory of our nation. All right. Think about some of the people who have died from this disease. Well, all right, here's my shire, here's the double helix, here's the paper, I'm going to backtrack, I'm going to keep my time. Look at the list of people who died from this disease, right? Vice President Biden, then President Biden, did not enter the political race because his son died in 2016. Senator McCain preserved the Affordable Care Act after being diagnosed with glioblastoma. That changed how he voted on preserving it. Right? Maya Love, the first African American congressional representative, died of this disease very recently. Gershwin died from this disease. Right? Remember, inform and entertain. There is, when Senator Kennedy died from this disease, the Democrats lost their supermajority in the Senate. This disease has a predilection for individuals who have been more educated, more socioeconomically advanced, and in fact has impacted the political trajectory of the United States. That's the only point I'm going to make. Everything else you guys know. So my journey, right? So this is a map. This is Bilbo's journey from the Shire to Lonely Woods, and this is Rollo's journey to Mortar. Right? I promise you'll show you a couple pictures. So I got to show this other picture. It's not science, but guys, remember this picture? Right? This is when Galadriel and Gandalf fought Sauron. Right? Anyone know what the light Galadriel was holding up is? Look at me. Gotta entertain. You tell me afterward. All right. So my battles, right? So the first thing that really started my journey was I did a surgery. This is a glioblastoma that I took out. Right? I did a good job. I really did a good job. This is a growth zone resection, right? The way we treat glioblastomas is we wait 6 weeks. We wait for radiation, right? You have to wait for the patient to heal first. Guess what? Getting the MRI before radiation, that tumor grew right back. Grew right back within 6 weeks. When we look at studies across the board, 80% of glioblastoma patients after growth zone resection will have some amount of growth. This is an extreme example. Okay? So my thoughts are, well, as a surgeon and someone interested in DNA repair, what can I do to avoid this? How can we treat this, right? So I came upon the concept of brachytherapy. This used to be very popular in the 80s, right? Everybody was doing it. It's basically, at the time of surgery, you insert these radioactive seeds into the tumor cavity. The idea being you don't have to wait for the tumor to grow back, right? The problem was there's 2 less than well-designed randomized control studies that failed, and people became less interested. You know, never mind that those studies were under-sampled and poorly designed, right? But failure is a failure. So what are the advantages of brachytherapy? Well, time. Well, certainly you avoid that wait, right? You could escalate the dose. Brachytherapies are very short-ranged. You could deliver up to 120 grays of radiation in the region of the resection cavity. You cannot possibly do that using external beam. You would just fry the skin and fry the bones. Comfort. A lot of the times, in certain situations like brain metastasis, the patient do not have to come back for radiosurgery. You don't have to come back to the hospital 3 to 4 to 5 to 6 times after the surgery. The radiation is done. And there are data that suggests that local high radiation in the resection cavity can induce immune responses in a way that produces something called a scalpel effect, which is that the immune system actually recognizes the tumor so that they can fight it off subsequently. So those were the reasons why I was interested. So, you know, I graduated in 2009 or so. Back then there were tools that allows us to deliver radiation. So I wrote IRBs, did all the various things. This is what's called gliocyte. This is what's called mammocyte. What it is you can do a resection, and then you can insert a balloon, inflate the balloon, and then deliver radiation into that balloon to give that high dose radiation. We published, this is 4 or 5 years of work, and this is only about 15 patients. That took about 4 to 5 years for the residents. Things take time, right? And we were able to show that per RPA class is a way to stratify how the patients are doing, right? If they're doing really poorly, they have a higher RPA class, they live shorter. Across RPA classes, if you had employed this method that we developed, patients do better. So that's all good. The problem, one day, these balloons are filled with radioactive liquid, and someone in radiation oncology dropped one of these vials and contaminated the entire department. Not a good thing, right? So the radiation oncologists were not happy, and we have to figure out another way to do this, right? So this is when I kind of reached out. This is kind of my next phase. Reached out to my colleagues at the Barrels, and what they were doing, I participated in this, but they really designed this, was instead of using these radioactive seeds, which are very difficult to place, you could imagine if you place 2 seeds too close to one another, the overlapping dose will cause excessive damage. So what they did was they said, well, let's put it in collagen. This is gel foam. This is something we use all the time. So what they did is they just put these radioactive seeds into gel foam. We designed this together. This was actually a company founded by Dr. Brackman. And we did an IRB, and we tested this in a pre-commercial before it was FDA approved. We did an IRB sponsor study. We showed it was safe. We showed that it actually helped some of the patients. Published this as well. While we were waiting for FDA approval, we ultimately got FDA approval in 2017, 2018. I shouldn't say we, I'm not a part of the commercial entity, just to be clear. We published other papers justifying, asking people to reconsider the use of brachytherapy, right? We looked at the SEER data set, and we showed that within that data set, if you control for all the important variables, brachytherapy still is associated with longer survival than without. Okay? And ultimately, this was approved in 2018. I was the first to use it in Minnesota. We used this to treat a number of patients, show the safety, show that there is a signal in survival, and that's all the way to 2022. In 2022 and 2023, I developed a clinical trial. This is a trial that we have up and running, the Gestalt. This is near completion in terms of accrual. And we treated a number of patients to identify the best sort of protocol. And so these were published. This protocol is almost at completion in terms of enrollment. So as we looked at the patients that we treated for this patient, this particular protocol, we noticed the following, which is very interesting, right? Learning from our mistakes. We went through the dragons and the journey, we're coming back home, we're reflecting on what we learned. If you look at these three pictures, these are pictures of failures, right? Tumors that grew back after brachytherapy treatment, right? You will see the heavy dose of radiation is shown in green here. Okay, so look at the green radiation dose. What you will notice is what failed is outside of the radiated area, right? And it's focal. It's not that it's all the way around, but there's like a spot in there, a spot in there, a spot in there outside of the radiation area, right? So what do we make of this? What's our reflection? What's the there and back? I thought that if this is because you sterilize the field inside and the tumor is growing outside, there should be more uniform tumor growing outside, not just in one focal area. Okay? So what could this be? We thought that what this might mean is the tumors are actually migrating away from the radiation. And as they migrate away, the brachytherapy gets less and less intense, right? So there's this concept of chemotaxis. We all know this. Cells will migrate away from noxious stimulation. Noxious chemicals, chemotherapy, they migrate away, right? So we asked the question, is there the equivalent of that? And we term this radiotaxis because it actually happens. To follow up on the failures, right, learning from our journey, we use that knowledge to design a collagen metric where we can monitor the cells to move in real time. You can see the cells moving. It's kind of cool how fast they're moving, right? And we place the seed in one area. So in this case, the seed's placed over here. And we ask the question, is there directional movement, right? And indeed, there is. So we're coining a new phenomenon called radiotaxis. And in fact, we've now identified drugs, right? Just like Dr. Lin, author, we now identify drugs that prevents the tumor from migrating away, with the goal eventually of eliminating these spots and enhancing the efficacy of our treatment. Now, is brachytherapy the cure for glioblastoma? No, there's going to be diseases outside of what we could treat. But the ability to maintain the patient's quality of life for a long duration of time allows other therapeutics such as immunotherapy to work. So ultimately, the cure for this disease will be a multifocal approach. So we did our journey, right? We traveled to Mordor, fought through a clinical trial of the tumor. We learned some things, we came back, and now this is one of the last scenes of The Lord of the Rings when Frodo leaves the Middle Earth, right? That was a little sad to see that scene for me. But this is going to be our next phase of our journey. So with that, I'm going to end my talk. So I'm going to have, I think Dr. Wu